If you've ever owned an EV, you know the feeling. I mean, it's a total cliche at this point.
Oh, absolutely.
If you're on a road trip, you're low on battery, it's pouring rain, and you pull into this dark, deserted parking lot behind a random strip mall. You find the single charging station, and the screen is just blank.
Right. Or somebody's parked in this spot.
Exactly. Or, it's charging at a mind-numbing 30 kilowatts, and you legitimately have time to watch a feature-length film before you can get back on the highway.
Yeah, it was an era totally defined by logistical anxiety. I mean, the entire electric vehicle ecosystem was trapped in this frustrating limbo where the cars were advancing way faster than the infrastructure could support them.
But looking at the stack of data crossing our desks today, from academic journals on power electronics to industry intelligence from Autotech's Insight, Daily Mosaic, Elaport, and Mercedes-Benz, it's like we've stepped into a parallel universe. So welcome to another deep dive into the source material.
It really is a completely different world now.
It is, because as of early 2026, we are officially looking at a landscape where the era of charging anxiety is basically dead.
The conversation has entirely shifted from scarcity to abundance. It's no longer about, simply finding a plug. It's about managing massive amounts of raw power, re-engineering the local power grid, and really turning that 15-minute wait into a premium hospitality experience.
Right. So whether you are planning a massive cross-country road trip or maybe considering picking up a used EV, or you just love bleeding-edge infrastructure tech, this deep dive is going to completely reframe how you think about the refueling experience.
It really will.
And to understand how most things have changed, we really have to look at the sheer brute force speed of the new systems coming online right now.
Yeah, the numbers coming out of 2026 are just staggering. I mean, to put it in perspective, look at BYD's flash charging launch.
Oh, the Paris one. Yeah.
Exactly. They did this massive reveal at the Palais Garnier in Paris back in April. They are now delivering up to 1,000 kilowatts. That is 1 full megawatt per individual cable in Europe on CCS2.
That's just an insane amount of power.
It is. With their Denza Z9 GT model, a driver can charge from 10% to 97% in just 9 minutes.
Wait, 9 minutes for almost a full charge?
9 minutes. And even in freezing, like minus 30 degrees Celsius weather, it only takes 12 minutes.
Wow. See, charging older EVs was like downloading a massive file on a dial-up connection. You just had to sit there and wait. These new Megawatt systems are like plugging directly into a fiber optic backbone. It's a massive uninterrupted data dump, but for physical electricity.
That's a great way to put it. And European manufacturers are pushing those exact same boundaries.
Yeah.
Mercedes-Benz has a rolling laboratory out on the roads right now.
Built on a van, right?
Yeah, a V-Class van. They call it the ELF, the Experimental Charging Vehicle. And it's testing 2 different extremes. First, it features a standard CCS connector, combined charging system plug that we've used for years. But they've cranked it up to push 900 kilowatts.
Which is huge.
It adds roughly 100 kilowatt hours of energy in 10 minutes.
Which is basically filling a massive long-range battery from empty to full in the time it takes to buy a coffee.
Exactly. But Mercedes didn't stop there. The ELF also has a heavy-duty megawatt charging system port. Now, that MCS standard was normally meant for massive commercial semi-trucks, but they're using it to test the absolute thermal limits of passenger EV components.
Just to see what happens.
Right. They even took their concept AMG GTXX to the Nardo test track in Italy and hit a blistering 1,041 kilowatt peak during testing.
Okay, let's unpack this. Let's look at the physics of this for a second. If I push 1,000 kilowatts of raw electrical energy through a cable into a car, why doesn't the hardware just vaporize?
That is the million-dollar question.
I mean, pushing that much current through a standard copper wire would generate so much friction and heat that the cable would just melt, right?
What's fascinating here is that you're totally right. Pushing 800 to 1,000 amps creates immense thermal friction. If you tried to build a traditional copper cable thick enough to handle that without melting, it would be so heavy a human being couldn't lift it off the station.
Oh, let alone plug it into a car.
Exactly. So the hardware had to evolve. The charging cables attached to these megawatt stations actually have chilled liquid pumping through them constantly.
Like a liquid-cooled gaming PC.
Very similar. The liquid absorbs the heat from the electrical friction, allowing the cable to remain relatively thin, flexible, and cool to the touch.
Okay, so the liquid cooling handles the physical cord. But what happens when that fire hose of energy actually enters the car? How does the vehicle's internal inverter survive a 1 megawatt hit?
So the survival of the car relies on a massive shift in semiconductor materials. This is detailed heavily in our academic journal source on power electronics.
Right.
For decades, the tech world relied on traditional silicon for its microchips and inverters. But silicon hits a strict physical wall when you throw high voltages at it.
It just can't handle it.
No, its atomic structure creates too much electrical resistance, which generates massive amounts of wasted heat. If you hit a silicon inverter with a megawatt charge, it would literally incinerate.
Which means they had to invent something completely new to route the power.
Right, so the industry transitioned to what are called wide bandgap semiconductors, specifically materials like silicon carbide and gallium nitride.
Okay, wide band gap?
Yeah, the band gap refers to the amount of energy required for an electron to jump and conduct electricity. Because these new materials have a wider band gap, they can handle 800-volt to over 1,000-volt systems effortlessly.
Oh, well, that makes sense.
They have incredibly high switching speeds, meaning they convert and route power with drastically less energy loss.
Okay, so we've liquid-cooled the cable to save our hands, and we have silicon carbide inverters to stop the car's electronics from melting. But you still can't just blast the chemical battery cell itself at full volume the entire time, right?
You cannot. And that brings us to the charging curve, which the academic journal explores using a Tesla supercharger V3 power curve as a really good example.
Right, the older V3 architecture.
Yeah. When you plug in, the station doesn't just push a flat rate of power. It starts out pulling a massive peak amount of energy, say 250 kilowatts on that V3, when the battery's state of charge is very low. But as the battery fills up, that power dynamically throttles down.
But why the throttling? Why not just keep blasting it with the full megawatt from 0 to 100% and finish the whole process in 2 minutes?
If the power didn't taper off as the battery got full, you would trigger a phenomenon called lithium plating.
Lithium plating?
Yeah, so inside the battery, lithium ions are traveling from the cathode to the anode. When the battery is nearly full, there is less physical space for those ions to settle into the anode structure.
Oh, okay.
If you force them in too fast with high current, they literally get jammed. Instead of absorbing, they turn into solid metallic lithium on the surface of the electrode.
Which permanently kills the capacity of the battery?
It drastically reduces the lifespan, yeah. And worse, those metallic deposits can grow into tiny spikes called dendrites.
That sounds bad.
It is. If a dendrite pierces the separator inside the battery, it causes a short circuit, which leads to thermal runaway.
Oh, wow.
Yeah, that is the clinical engineering term for an uncontrollable chemical fire.
Uncontrollable chemical fire. Good to know. It's exactly like pouring a beer.
How so?
Well, you can pour the liquid really fast at the beginning when the glass is completely empty, but as the liquid gets closer to the rim, you have to slow down to a tiny trickle, or it foams over the edge and ruins everything.
That's a perfect analogy.
So the car's internal battery management system is basically an expert bartender, constantly adjusting the pour rate based on thousands of calculations a second so the battery doesn't foam over into lithium plating.
Precisely. The power electronics are communicating with the station in real time, dictating exactly how much current the chemistry can handle at any given millisecond.
That makes total sense. But, zooming out from the car itself, this megawatt era presents a terrifying logistical problem.
The
grid. If I'm driving through a quiet suburban neighborhood and I pull into a station and another driver pulls up next to me and we both start yanking a megawatt of power out of the grid simultaneously, we would instantly destabilize the local electrical grid.
It's actually worse than a neighborhood blackout. Pulling 1.5 megawatts unannounced can literally fry local substations.
Wow.
A connection of that size is enormous. In the past, it could take years just to get the permit from local utilities to pull that much power, and the physical infrastructure upgrades required, like new transformers, thicker municipal lines, they cost an absolute fortune.
Right.
You simply cannot plug a dozen of these megawatt stations directly into a standard municipal grid.
Which begs the question, how on earth are networks deploying thousands of these stations across Europe and North America in 2026?
They're completely decoupling the charger from the grid.
Decoupling it.
Yeah, they're using massive battery buffers. Look at those BYD flash charging stations we mentioned earlier. Instead of yanking a megawatt straight from the city power lines when you plug in, the charging station itself houses 290 kilowatt-hour Blade Battery 2.0 packs hidden inside the casing.
Oh, I see. So the station is slowly sipping power from the local grid 247 at a low, stable rate and storing that energy up in its own internal batteries.
Okay.
Then, when I pull up in my car, the station dumps the power from its batteries into my battery. The municipal grid barely even registers that I'm there.
It's the ultimate infrastructure hack. Huawei showcased this beautifully at Auto China 2026.
Oh, what did they do?
They rolled out a 1,500 kilowatt system, but they specifically did not position it as just a car charger. They called it a full stack infrastructure solution.
Okay.
It hooks those heavy-duty liquid-cooled units up to a massive 215 kilowatt-hour DC energy storage module, which can also integrate directly with solar panels on the station's canopy.
See, this highlights a really fascinating philosophical split in the industry right now. Huawei is essentially saying, the electrical grid is old and broken, so we are going to fix the station.
Right.
Meanwhile, battery manufacturers like CATL, with their Shenzhen battery system that claims a full charge in 6 minutes, they're saying, we are going to fix the car's internal chemistry to accept power faster.
If we connect this to the bigger picture, that fix-the-station approach with battery buffering is quietly saving the industry billions of dollars.
Because they don't have to wait for the utility company.
Exactly. Beyond avoiding the cost of new utility lines, it saves operators from crippling demand charges.
What are those?
Utilities charge large commercial properties not just for the total energy they use, but for the absolute highest peak of power they draw at any single moment. If a station pulled 2 megawatts directly from the grid for just 10 minutes, the utility would hit them with a massive financial penalty. Battery buffers smooth out that draw, keeping operational costs radically low.
So, by fixing the grid issue with battery buffers, suddenly anyone can build a hyper-fast charging station almost anywhere, even in a rural area with weak infrastructure.
Yeah.
And that sudden democratization of charging is exactly what ended Tesla's decade-long monopoly. Let's talk about the actual human experience of you, the listener, pulling into a station today because the landscape has completely flipped.
It really has. For a very long time, Tesla's supercharger network was their ultimate moat. I mean, people bought the cars specifically for access to the reliable network.
Right, because everything else was broken.
But looking at the 2026 data out of France from our daily Mosaic source, the moat has basically evaporated.
Wow.
France recently crossed 192,000 public charging points, delivering a massive average of 788 kilowatt hours per point. And in recent user experience rankings, Tesla completely dropped out of the top 5 networks.
That's wild. Independent networks like LaPlane, Mobilize, and Fastened are overtaking them in user satisfaction.
They are.
And a massive driver of this is the interoperability reality we're living in. The era of the walled garden, where you could only charge your car at your specific brand's plug, is over.
Yeah, every major manufacturer, Ford, GM, Volvo, Mercedes, they all agreed to use factory-approved NACS adapters.
The North American Charging Standard.
Exactly, which was originally Tesla's proprietary plug, but is now essentially universal. A driver in a Ford can pull up to a Tesla station, plug in, and charge flawlessly.
And it goes beyond just the physical plug fitting into the hole, right? The software is finally unified. We are seeing the... So what does this all mean? If the plugs are universal and the software is invisible and battery buffers mean anyone can offer megawatt speeds, how do these different charging networks actually compete for your business?
That's where it gets fun.
Right. Because electricity prices are stabilizing, our sources note the network Electra is charging a flat euro 0.39 per kilowatt hour with absolutely no subscription required. So the battleground has completely shifted. Operators have to compete on what the industry calls the quality of stay.
Yeah, since the physical act of charging has become a standardized commodity, networks are fighting over hospitality. They want to know what you are doing during those 15 minutes your car is plugged in.
And the solutions they are building are incredible. Like a company called Bike World is deploying these modular high-tech lounges directly onto charging sites.
Oh yeah, those are cool.
They feature 24-hour amenities, clean restrooms, and self-serve pizza machines. And then Fastened is building massive flagship hubs with 32 solar canopied stalls, pristine showers for long-haul truck drivers, and dedicated outdoor play zones for families.
It is a complete evolution of the space. EV charging has transformed from a stressful, isolated chore in a sketchy parking lot into an experience that mirrors a premium highway rest stop. It finally respects the driver's time.
But, you know, if the public station is evolving into a premium lounge, what happens when you aren't on a road trip? What happens when you are parked at home or when a logistics company is running a massive fleet of commercial vehicles? Can we eliminate the physical plug entirely?
That introduces the concept of bidirectional charging, specifically vehicle-to-grid and vehicle-to-home technologies.
V2G and V2H.
Exactly. The fundamental idea is that power doesn't just flow into the car, it can flow backward out of the battery to power the world around it.
We see this deeply integrated into the Mercedes ELF van project, right?
We do. A typical EV on the market today houses a 70 to 100 kilowatt-hour battery. With bidirectional charging hardware, that single parked vehicle has enough stored energy to power an average home for 2 to 4 full days during a blackout.
That's incredible.
It is. By intelligently managing when the car draws cheap power from the grid at night, and when it pushes power back into the house during expensive peak hours, Mercedes estimates a typical household could save roughly €500 a year in energy costs.
Here's where it gets really interesting for me. Mercedes is conceptualizing this idea of a virtual energy account.
Oh, this is fascinating.
Right. Imagine you have solar panels on the roof of your house. On a beautifully sunny Tuesday while you are at work, your roof generates excess solar power, and it stores that energy directly into your car's battery in the garage. The Mercedes system meticulously tracks those specific electrons, granting your account energy credits. Then on Saturday, you are driving across the country and you pull into a public fast charger. You can literally use the credits you generated from the sun hitting your own roof to pay for your fast charge on the highway.
It completely redefines what a car is. I mean, it is no longer just an isolated mode of transportation. It is a distributed mobile node in a global energy network.
Yeah.
And as these vehicles become more autonomous, the actual physical act of charging is being automated out of existence.
The new Porsche Cayenne Electric is a perfect example of that. It is the first series production passenger car offering a massive 11-kilowatt wireless inductive charging pad.
Just drive over it.
Exactly. You just pull into your garage, park directly over the pad on the floor, and the magnetic field charges the car wirelessly. At around $5,000 to $6,000, it is a premium option right now, but it completely removes the human labor of plugging in.
And in the commercial sector, where human labor is a massive operational bottleneck, automation is even more aggressive. We are seeing the rise of heavy-duty robotic charging arms.
Like actual robots plugging in the cars.
Yeah, a company called Roxys is rolling out incredible hardware. Their M1 system is a multi-bay overhead robotic arm designed to automatically charge fleets of driverless robotaxis without human intervention.
Wow.
They also developed the Steward S2, which uses advanced computer vision to autonomously plug heavy-duty megawatt cables into commercial trucks at busy port terminals and logistics hubs.
It is wild to think about how much ground we've covered today. I mean, we started with the sheer violence of a 1,000 kilowatt charge.
Okay.
We explored the physics of liquid-cooled cables and silicon carbide inverters that prevent the cars from incinerating. We looked at how battery-buffered stations protect our fragile municipal grids, how the death of exclusive plug standards paved the way for interoperable pizza lounges, and finally, a future where your car acts as a mobile solar battery for your house while robotic arms handle the cables.
A lot.
It is. The entire landscape has fundamentally shifted to prioritize your convenience and your time.
It is undeniably an engineering triumph. However, the deep integration of this technology raises an incredibly serious question.
Oh, right.
Because these charging networks are now structurally tied to our daily transportation and to the power grid itself, they introduce a massive new vulnerability.
And our final source from Elaport details the darker side of this hyperconnectivity.
Yeah, because EV networks pull so much power and affect so many citizens, the European Union has officially classified electric vehicle charging networks as critical infrastructure under the strict NIS2 directive.
Which means they have to be protected like power plants.
Exactly. And this is not theoretical panic.
Yeah.
In 2025, there was a highly coordinated cyber attack that targeted Polish wind and solar farms, attempting to manipulate their power output to destabilize the grid.
Wow.
Following that event, charging stations must now adhere to heavily penalized cybersecurity laws.
It makes terrible sense. I mean, if your car is plugged into a charger and that charger is talking to the local utility grid to manage power flow, and millions of these are connected simultaneously,
Yeah.
a bad actor taking remote control of that charging network could manipulate the power draw. They could theoretically force millions of cars to pull a megawatt of power at the exact same millisecond, which would cause a catastrophic frequency drop and crash the national power grid.
This raises an important question on it. We have solved the physics of the battery, and we have solved the logistics of a charging station. But we're leaving you with this to ponder. As our cars evolve from simple vehicles into highly connected, megawatt-pulling extensions of the national power grid, could the next major target for global cyber warfare be the quiet, high-tech charging lounge right down your street?
It is a sobering thought to take with you the next time you plug in and grab a coffee. Thank you for joining us on this deep dive into the source material. Keep learning, keep questioning the systems around you, and we'll see you next time as we continue to navigate these fascinating technological shifts.